Professor John Gales from York University will give the next presentation. Thank you, John, and the floor is yours.
Great. Thank you, Thomas. It's great to have seen all the presentations earlier on. I'll just kind of start with a little bit of a disclaimer. When it comes to this particular presentation, my colleague Matthew Smith, who's an associate at Intuitive, is actually responsible for the SAFIR modeling that we're going to see today. So if you have very critical questions, I would encourage you to send them to him. If you have some disagreements with some of those approaches or whatnot. But I'll do my best today to talk a little bit about these aspects. When I looked at the program, there wasn't that many speakers from North America. When it comes to me and Thomas, we kind of have a lot of European background too, but I think that feeds into what I'm going to talk about today too, which is Canada and performance-based design implications with steel structures. So diving in to this. When we think about Canada, actually, when it comes to how we approach fire design, it's especially for steel and concrete and such, it's very traditionally prescriptive, and it's been that way for quite a bit of time. However, within the Canadian building codes around 1995, they started to shift towards objective-based design. And by objective-based design, it's similar to performance levels where the acceptance criterion is basically to compare your design to whatever the prescriptive solution would show. So when that was developed, the steel standards started to adopt guidance that would follow that. However, there wasn't really a large educational framework, and there really wasn't a transition of research that was happening in Europe, reaching over into Canada very much to kind of come up with innovative solutions. So most of the steel structures that would use the objective-based design that are documented and published would be basically sizing up the steel member. They would make it larger to meet those processes. There wouldn't be the process of optimizing fire protection because those methods, like even in Europe, they really weren't being developed until the early 2000s or so, but they weren't trickling over to Canada, and the idea of optimizing fire protection just wasn't happening. So when I went back to Canada from studying in the UK, uh, I initially reached out to Intuitive, which is the company that was involved in this work. And we started to develop a framework about how we could try to find ways of bringing modeling techniques, design ideas that were being used in Europe over to Canada that would fit within the current code system and standards. And at the same time, that obviously had a lot of people really interested. So the steel industry was very much wanting to support this trajectory. And one of the things that they had proposed was that if we wanted to educate Canadian fire engineers, they needed a Canadian resource that was based on Canadian codes. And same thing with practitioners. So the Canadian Institute for Steel Construction wanted to have basically a textbook created that was basically, here is how you interpret the current codes, here is what you could do with these current codes, and here are some examples of how you could go about doing that. And that's basically when Thomas reached out about discussing, it just so happened we use SAFIR to do our examples that would be used within this resource. And the resource has just been submitted to the publisher. The contents is basically here, and what I'm going to talk about today is a lot about competency because in the Canadian system, we have to get our engineers up to that level. And then I'm going to talk about the examples we chose to include within this book. So I'm not going to go through the whole book, but it is more tailored towards Canadian engineers and Canadian students with it. But there's certainly things that you can take away and use internationally with it. To talk a little bit about the Canadian Code itself, when we're dealing with steel structures, we're dealing with a standard that's called Annex K, which is actually a mandatory component that you have to follow. I already mentioned just briefly that when we do our objective-based code, essentially we have to be in compliance with the prescriptive code still, but we can create an alternative solution. Basically, we can have something that meets the criteria. So a simple criteria that could be checked is like deflection, the expected deflection that would be coming out of the prescriptive requirement. Are we meeting that in the performance requirement and such? And one of the examples that I'm going to show today too, this doesn't necessarily mean that you're cutting back structural fire protection. In some cases, it actually means that you're going to have more, which is one of the examples I'll show that comes out of this particular framework. The challenge that comes with the Canadian Code, and one of the things that I always get burned on when I do academic papers, is they're saying, why do you keep comparing to the standard fire? And if you've read some of the work that I have about the standard fire, you'll know that I'm very critical about it, but we still have to show that as one of our comparators when we're running the analysis under the system. So the standard fire is something we have to work with. We can use other design fires, but we still have to use the standard fire as our baseline. So there is a lot of aspects to that. So Annex K is within our steel handbook, and it lays out the procedures of what you can do for Canadian design and the particular bouts of theory that come through. The good news for international people looking at our standards is they're highly based, at least on parameters that come out of Eurocode. So the principles of material factors are all coming from there. The challenge with the design basis fire that we're dealing with is it is very prescriptive with the standard fire, but it does start getting into parametric fires, and there's a little bit of allowance to be thinking about traveling fires. When we look at the design requirements, there's simple methods that there is some guidance for, and then there's advanced methods. But the annex doesn't tell you how to do it. It just says this is what you have to meet. So when it comes to promoting fire design in Canada, that's particularly why there's interest by the industry to have published examples of ways that you can do advanced methods. And I'm not going to talk about the simple methods that we've put into the book today. They're very basic, how to do a truss member, how to do a column or something. When it comes to advanced methods, you're getting into membrane actions, bilinear columns, which is the focus of what I'm going to go into today. We could take a lot of inspiration from the US because there is a number of equivalent resources over there. The challenge that we have in the Canadian system with steel structures and design is it's not necessarily the same motivators for steel that is in the US. We do like to be different, as you would have heard in the news in Canada. And there are different steel trends that happen in a lot of our communities that isn't necessarily the same. There are overlaps with it, but we were trying to make something Canadian specific when it came to this. So we use SAFIR. And why did we use SAFIR? This decision was over 10 years ago. We started this project in 2013. We sent multiple emails to Thomas asking for advice about using the software as we were going through this journey. And we use SAFIR particularly because of the text inputs and outputs that we could be generating with this, because we had an eye on integrating some of this modeling with building information modeling. I wish we could have gotten far with that, but that was one of our early goals, is we wanted to see if we could keep things open from it. So no means to endorse SAFIR, sorry. But in the case of what we were trying to do, it made the most sense to be using it for education and demonstration to practitioners, as opposed to some of the other packages, because we're trying to get Canadian design to be more open to fire design. We wanted a package that also had a lot of resources about validation already, so that it would be easier for authorities having jurisdictions to trust the software more. So that's why we went this route. And it's not the only thing that you can do with steel structures. The first thing in our book is a benchmark exercise that we use SAFIR for. And a lot of Canadian practitioners really don't know anything about Cardington. So we illustrate membrane action within the book about using the Cardington data. And we illustrate to the practitioners and students that a lot of this data is freely available or can be obtained. So it's not within out of reason for people to be trying to do their own verification and validation. It also allowed us to really go into an aspect of what is actually different between Canadian design of a composite flooring system to what you would see in Europe and maybe even in the US. And we have a very different type of rebar mesh that's utilized in Canada that does have implications or potential implications to membrane action. There's a different type of shear connection that comes from the composite system, and even the concrete type is usually very different when it comes to these systems. So we use the European data, the material data that is coming out of Cardington, and we run a verification validation exercise for people to go through using SAFIR and walking people through step by step of how you would do this analysis. We used one of the corner tests to do this illustration, and we looked at displacement. There's many things that you can be looking at for acceptance criteria, but for our examples, we kind of focus in on particular acceptance criterion just to show these ones. But there's way more into the actual design that you would look at. We then take it further. We start with there, and then we try to show an advanced method. And this is actually it was a building that was going to be developed in Toronto. And we selected it as a demonstration exercise because it had principles that came from the UK. It was a British architect who designed the building, but it was not, the fire design was a prescriptive solution. There was no performance or objective design in reality. So we knew that you probably could use that here. And we wanted to demonstrate what would happen if the secondary members of this particular floor plan would have no fire protection coating. What would that mean to the deflection and connection forces that would develop in this particular one, and then show a demonstration of membrane action in the system. It was a very lengthy steel beam. We're talking about a 15-meter long steel beam, so the deflections that are going to be observed are going to be very large. So when you see some numbers here that I'm about to show, don't get that scared. They are big, but the span is also incredibly large with it. We wanted to show to Canadian practitioners traveling fires methodologies as well. And at the time, we used the ITFM. We also used parametric fires. And of course, we had to compare back to a standard fire as well with this. And the book contains basically analysis of the deflection that was coming from these separate analyses based on those thermal exposures that we were expecting to see. And these are some of the parameters. And the connection forces that we observed, our connection is assumed to be very rigid. So we do get fairly large forces being generated. This led to a bit more research with experimental stuff that I'll show as we close this presentation. The second exercise is actually something new. Instead of Cardington and te tensile membrane action, I shouldn't say it's new. It's really we're behind in Canada, but bilinear columns for a lot of architectural actions are starting to trickle into the Canadian market, particularly in the Toronto area. And there was a particular building that was going to be proposed to use these. And we wanted to do an illustration as to what would happen if you did have a bilinear column, because traditionally the fire resistance coatings wouldn't necessarily capture the added axial forces that can be transmitted due to the angle of the system. Now, what you see in these diagrams, the angle is very grossly exaggerated to how much you actually have there than in reality. And we looked at each floor that had the bilinear columns and in different configurations. Ran some baseline 2 hour. This building needed a 2 hour rating. It was proposed to be about 54 stories or so. And we figured based on this particular example, it would be one where you would have to use an advanced solution, but it's likely that you're not going to be removing fire protection, that you're going to have to actually be increasing the fire protection in this example. And it's kind of a nice way of talking about standard fires and resistance ratings to actually what happens with time when it comes to some of the plots. So we look at the 12th story and the 6th story to look at the particular configurations that are going. And again, in this case, we're looking at the column movement as well as the deflection of the system. And we do get on a baseline, we do get a failure predicted with the 2 hour amount of fire resistance coating before 2 hours are being met. And then in order to actually achieve the required 2 hour fire resistance rating, they have to apply 3 hours of equivalent coating to the system is where that was going to come in. So it was a really nice example of the for the book is not to make people think uh, I'm going to remove fire protection all the time, but there is a requirement that you may actually have to add even more into the system and educate people about some of these more advanced configurations are going to need that type. And we looked at each floor. In some cases, originally they wouldn't have failed. So it was a pretty good exercise when it came to it. It led to a research question because bilinear columns actually don't have a lot of experimental data associated to them. So our friends at the steel industry helped us procure some steel. And this project is still ongoing. We're looking at different connection types and different horizontal thrusts onto the systems to see what kind of actual connection forces we actually do observe from the expansion or contraction of the steels in cooling. So it's a pretty robust test program that's still ongoing. We're using narrow spectrum illumination technologies, which is you illuminate a material with a very high blue light wavelength, and then your cameras have a filter on them that removes color above blue, and that allows you to see through a fire flame to measure things like displacement and uh, uh, strain events, which has some really good modeling implications down the road. So we're kind of excited where that's going to end up, and that experimental program is just kind of concluding. The big challenge in Canada is competency. We have a very limited number of fire programs in Canada. We have a good one at Waterloo that my university is very closely affiliated with. There's a program in Carleton, and then outside of that, you just have a very few number of courses that are happening. To train students, it's a challenge. So having some resource documents for people is really important. Within Canada, at least, we have a very high regulation of professional licensure. That if you want to undertake fire engineering and design, you actually have to show that you have some level of training in it. Otherwise, you can actually be found for professional misconduct with things. So there's some safety nets that are in there for competency, but definitely it's a very big thing that has to happen, especially as you're trying to grow parts of this industry. There's contributors to this project within the book. There's a fire modeling review of different techniques for steel. Chloe is running the experimental program. Panos Kostavinos performed the peer review of the book. Our steel comes from Benson Steel, and our funding comes from the Institute of Steel Construction on this particular project. And as I mentioned, if you don't like what I'm doing with the SAFIR model and the assumptions that we're making with it, or I can't answer a particular question, Matt originally was planning on him doing this presentation, but he is very busy right now. So you can contact him at Intuitive, and I'm sure he'll be happy to answer any of those types of questions. But beyond that, thank you so much for having me here today. Yeah, I'll try my best to answer what I can.